Now, what do we actually do with those counts? This is essentially what we do. We work out things called richness or abundance or evenness or Simpson's diversity index. We're not going to go over things in too much detail because you'll be practicing them in class, and there'll be some individual videos showing you how to work out some of these, but I'm going to go through the basics now. Richness is essentially, its symbol is big S, and richness is essentially the number of species in an area, not the number of individuals, how many species you have in an area. So a desert ecosystem might only have 10 species in it in a radius of a couple of kilometers, whereas a forest in like a couple of kilometers of area, they will have huge numbers of species, like possibly hundreds of species. So they are much more rich with species than, say, a desert ecosystem. Species abundance I've already told you about. That is the number of individuals for a particular species. So there might be 10 trees, 1 million ants, 100 different shrubs of the same species. Okay, so you have to do that with the little n symbol. That's its symbol. When you see big N, that means the number of individuals, and I don't care what species they are, just how many individuals does that area support. Okay, so that's what abundance is for total abundance. That's the big N. That's the total number of individuals, doesn't matter what species they are. And we use those numbers there to come up with a few other little calculations. Evenness is basically a relative abundance. It's where we look at the proportion of the individuals for one species compared to the individuals for the whole, or all of the individuals you find. And the easiest way to do that is just by doing it as a percent. Come up with that fraction there and times it by 100. There's also another formula that you can use with log in there. I've never had to use that before, and we'll only pull that in if this formula is required. But the one I really need you to learn about is Simpson's diversity index. So Simpson's diversity index takes into account the richness, so that is the number of different species that you have, and the evenness, which is your proportion of individuals to all the individuals regardless of species. And this is essentially how you work it out. Now there's going to be a separate video, because I had tech issues on this one, that actually goes through how to actually calculate this step by step. So I'm just going to point out the main factors. Essentially you have the number of individuals on the top, but you don't just count them up, you actually square them. So ignore the ones for now. Essentially, if I ignore the ones completely, it is a fraction of my individuals for a particular species. So it could be just the trees or just the grass. But I don't just count up their abundance, I actually square the abundance. So it's little n times little n. And on the bottom, I have the number of individuals for all of them, regardless of species. So how many individuals are in the entire quadrat area that you're sampling. And again, I square them, I times them by each other. The only other thing that we have here is this little -1 thing here that people get confused with. And the reason we have the -1, just going to erase that out, is it's essentially a fudge factor. Basically, when we compare in biology, if we did a census on an area compared to sampling the individuals in that area, and they've tested it out to see which one is more accurate, normally when we sample, we always tend to oversample. We always get a bigger number than what is really there. So they've added in this fudge factor, this -1. All it does is bring one of my little counts down by just 1. So you might have 100 different acacia trees there. We're going to turn that to 99. Or it could be 1,000 ants. We're going to turn that to 999 ants. If it's like 10 trees, it'll turn into 9 trees. So before we square 10 trees by 10 trees, we reduce one of those little counts down by 1, just as a fudge factor to eliminate the the problem of overestimating. So essentially, instead of going 10 trees by 10 trees, we go 10 trees by 9 trees. We reduce the proportion just a little bit because we know we always overestimate. Same thing with the total number of species, individuals on the bottom. We reduce one of them down by 1 just as a fudge to try and reduce and stop us from overestimating every time. And when you actually test this out in theory, in practice, it works. That fudge factor actually makes this formula more accurate in reality. So there'll be another video that I've pulled in for someone else that goes through how to do this in detail, because I don't have the pen function right now. But essentially that's what it is. It looks at the proportion of the square of the individuals, add them all up, to the proportion of all of the individuals on the bottom, and then we simply make that number, turn that number around with this -1 of everything we did there, and you get a Simpson's diversity index. And essentially, to interpret it, is essentially the bigger the number, the more diverse the system; the smaller the number, the less diverse the system. Okay, thank you very much for your attention. I know this has been a bit of a long video here. We'll put in little videos for examples so that you don't have to watch the whole video again. But the next video coming out will be on analysing the abiotic data.